Innovative technologies transform railway construction and repair, delivering safer, faster, smarter infrastructure for modern transportation networks across the future of sustainable mobility. The rail cutting process begins with the preparation of the work area to ensure stability and safety. The section of railroad rail to be cut is clearly marked, allowing operators to identify the exact cutting point. The rail is then secured to prevent vibration or movement during the operation, which is critical for achieving a clean and precise cut. The cutting operation is carried out using a H2 series rotary rescue saw equipped with a black diamond cutting blade. Once the saw is activated, the operator gradually brings the rotating blade into contact with the rail surface. Instead of forcing the blade, steady and controlled pressure is applied, allowing the high-speed rotation to do the work efficiently. As the blade penetrates the hardened steel, sparks are generated, indicating effective material removal. The black diamond blade maintains consistent cutting performance even under extreme friction and heat, enabling it to slice through the dense rail profile without losing speed or stability. The operator continues the cut in a smooth, continuous motion, keeping the saw aligned to ensure the blade follows a straight cutting path. During the process, brief pauses may be taken to manage heat buildup and maintain optimal blade performance. This controlled approach helps extend blade life and prevents damage to the cutting equipment. As the blade reaches the base of the rail, cutting speed remains steady to complete the separation cleanly. Once the cut is finished, the two rail sections are fully separated with minimal deformation at the cut edges. The saw is powered down and removed from the work area. The result is a fast, precise, and reliable full rail cut, demonstrating the effectiveness of the H2 series rotary rescue saw, combined with the durability of the black diamond blade in heavy-duty railroad applications. The process begins at the rail joint, where a bright silver section marks the exact location to be welded. This area has been previously ground by a worker to remove surface irregularities, oxidation, and contaminants. Grinding ensures that the rail ends are clean and properly aligned, which is essential for achieving a strong and uniform weld. Once preparation is complete, the flesh butt welding machine is positioned over the rail joint. The welding fixture clamps firmly onto both rail ends, holding them securely in place. Hydraulic rams mounted on the fixture are aligned with the rails and prepared to control their movement during the heating and welding stages. Electric current is then applied across the small gap between the rail ends. Pulsed alternating current, typically between 600 and 700 amps, flows through the contact surfaces. This electrical resistance generates intense heat at the rail ends. As the current continues, the steel at the ends of the rails rapidly heats up and begins to glow. When the temperature reaches approximately 1500 to 1700 degrees Fahrenheit, the steel becomes plastic and suitable for forging. At this moment, the hydraulic rams activate and push the two heated rail ends toward each other. The force applied by the rams causes the softened metal to fuse together, forming a single continuous rail. Excess molten material is squeezed outward from the joint, indicating that proper fusion has occurred. The newly formed weld remains visibly glowing, showing that the steel is still extremely hot. This glowing section confirms that the rails have been successfully fused at the joint. The welded area is allowed to cool gradually, stabilizing the structure of the steel and locking the rails into one solid piece. After the welding operation is complete and the joint has cooled sufficiently, the flash butt welding machine is released from the rail. The clamps are removed and the hydraulic rams retract. The welder is then packed up and moved away from the track, leaving behind a continuous welded rail section ready for further finishing or inspection. The video shows a traditional thermite welding operation used to join two sections of railroad rail into a single continuous track. The process begins with careful preparation of the rail joint. The ends of the rails are precisely aligned and secured to ensure correct geometry. A disposable sand mold is then clamped tightly around the joint area. This mold is sealed with heat-resistant clay to prevent any molten metal from leaking out during the welding process. Proper sealing is critical, as the temperatures involved are extremely high. Once the mold is in place, the rails undergo a preheating stage. Workers use a propane-oxygen torch to heat both rail ends evenly for approximately 5 minutes. During this time, the steel gradually reaches a glowing orange-red color, indicating a temperature range of about 600 degrees Celsius to 950 degrees Celsius. Preheating removes moisture, reduces thermal shock, and ensures good fusion when the molten steel is introduced.
I'll get you guys sharing it.
After preheating is complete, a crucible containing the thermite mixture is positioned directly above the mold. The thermite compound consists mainly of iron oxide and aluminum powder. When ignited, a powerful chemical reaction begins. Aluminum strips oxygen from the iron oxide, producing molten iron and aluminum oxide slag. This reaction releases an enormous amount of heat, reaching temperatures between 4,000 degree F and 5,000 degree F. As the reaction proceeds, the molten steel flows downward into the sand mold, filling the gap between the two rail ends. The liquid metal surrounds the joint completely, bonding the rails together at a molecular level. The aluminum oxide slag, being lighter, rises above the molten steel and remains separated from the weld area. After the mold is filled, the metal is left to cool and solidify. As it cools, the molten iron forms a solid, seamless connection between the rail sections. Once the metal has fully hardened, the sand mold is broken away and excess material around the joint is removed. The welded area is then ground smooth to match the original rail profile. The result is a strong, continuous rail joint capable of withstanding heavy train loads and constant vibration. Thermite welding remains a reliable and widely used method for railroad maintenance, especially in remote locations where large welding equipment is impractical. The Pandrol SB60 with AutoMaster is a modern and efficient solution for railway track maintenance. The SB60 is a high-performance sleeper changer designed as a carrier-mounted attachment, typically installed on an excavator. It is capable of removing ballast, extracting worn sleepers, and installing new concrete or wooden sleepers using a single attachment. Thanks to its tilt and rotation functions, the SB60 can operate effectively in confined areas such as stations, tunnels, or narrow track sections, allowing sleepers to be replaced from the side or the center of the track. In addition, the AutoMaster is an optional attachment that significantly enhances the machine's functionality. It allows the automatic installation of Pandrol fast clips, including FC and FE types, directly onto newly installed sleepers. This process is fully controlled from the operator's cab, reducing the need for on-track workers and improving overall safety. The AutoMaster can install approximately 20 to 30 sleepers per hour and is compatible with both SB40 and SB60 models. The R24 is a high-output ballast regulator designed to meet the demanding requirements of modern railway construction and maintenance, particularly on high-speed lines. Built on bogies, this powerful machine combines mobility, precision, and efficiency, making it an essential asset for large-scale track works, where consistent ballast quality and accurate profiling are critical. One of the key features of the R24 is its integrated ballast hopper system. The machine is equipped with a standard 10 cubic meter hopper, which can be expanded to 13 cubic meters. This large capacity allows the R24 to recover excess ballast from areas with surplus material and redistribute it efficiently to sections where ballast density is insufficient. As a result, ballast waste is reduced, and track geometry can be restored more effectively without additional supply operations. The R24 is specifically designed for high-output ballast profiling and regulation. Its plows shape and level the ballast accurately along the track, ensuring proper support for sleepers and rails. To enhance operational control, the machine can be fitted with a plow deployment monitoring system, allowing operators to supervise plow positions in real time and maintain consistent working quality. Powered by a 440 kilowatts engine, the R24 delivers strong performance while remaining highly mobile. It can reach a maximum self-propelled speed of up to 100 kilometers per hour, enabling fast transfers between work sites without the need for additional hauling locomotives. With a total weight of 68 tons, a length over buffers of 26, 500 millimeters, and 5 axles, the machine offers excellent stability during operation. In addition, the R24 features a spacious, customizable cabin designed to improve operator comfort and visibility, supporting long working shifts and precise control during ballast regulation tasks. On the 22nd of March 2017, a specialist team from Hay Rail arrived to carry out the stressing of the first 1,000 meters of continuously welded rail on the Gloucestershire-Warwickshire Steam Railway extension to Broadway. This operation is essential to ensure the track can safely withstand temperature changes and long-term loading. 2 anchor points are established, each consisting of 5 fully clipped-up rail panels positioned 500 meters on either side of a central pulling point. The size of the gap to be closed at the center is carefully calculated using several variables, including the total rail length, the rail section size, and the current temperature of the steel. To allow controlled movement during stressing, the rail is placed on small rollers at intervals of every 8 sleepers. Hydraulic rams are then used to pull the rails together with precise force, gradually closing the calculated gap. Once the correct stress level is achieved, the rail ends are welded together to form a continuous length. Finally, the entire section of track is fully clipped up, locking the rail securely in place and completing the reinforcement process. The demolition process begins with the systematic dismantling of the bridge's steel girders. Once all safety zones are secured and lifting equipment is positioned, workers prepare the main steel beams for removal by marking precise cutting points. These points are selected to ensure the bridge remains stable during each stage of dismantling and to prevent any sudden or uncontrolled movement of the structure. High-reach excavators, equipped with hydraulic shears, are then used to cut through the steel girders. The hydraulic cutters apply immense pressure, allowing the thick steel sections to be sliced cleanly and efficiently. Cutting is carried out gradually, starting with secondary beams and cross members that connect the main girders. Removing these components first reduces structural tension and isolates each main girder section for controlled lifting. As each cut is made, cranes positioned alongside the bridge take on the load of the steel sections. Lifting slings and chains are securely attached to the girders before the final cuts are completed. This ensures that once the steel is fully severed, the weight is immediately supported by the crane rather than falling under its own mass. Crane operators carefully adjust tension during cutting to maintain balance and stability. After separation, the crane slowly lifts the steel girder segment away from the bridge deck. Ground crews guide the suspended load using tag lines to prevent swinging and rotation. The lifted sections are then lowered onto designated staging areas or directly onto transport vehicles. Each movement is performed slowly and deliberately to avoid shock loads and reduce the risk of structural failure. The demolition continues sequentially along the length of the bridge. Main longitudinal girders are cut into manageable sections, typically starting from one end and progressing toward the center. By following this order, the remaining structure retains enough support while the removed sections are cleared. Continuous monitoring is carried out to check for deformation or unexpected stress in the remaining steelwork. In areas where girders are tightly connected or heavily reinforced, additional cutting passes are required. Workers may use oxy-fuel cutting torches to assist in separating thick steel plates or bolted connections. These torches generate intense heat, allowing operators to slice through complex joints that hydraulic shears alone cannot handle. Sparks and hot debris are carefully controlled, and fire prevention measures are maintained throughout the operation. Dust and debris generated during cutting are controlled using water sprays. These sprays reduce airborne particles and improve visibility for machine operators. At the same time, debris netting and exclusion zones ensure that falling fragments do not endanger personnel or equipment below the bridge. Once the primary steel girders supporting the span are removed, attention shifts to remaining steel elements such as bearing beams and end supports. These components are cut free in a similar manner, with cranes once again supporting the load before full separation. Each piece is removed individually to maintain full control over the dismantling process. The removed steel girders are transported to recycling facilities. Large sections are either directly recycled or further cut into smaller pieces to facilitate handling and processing. Recycling the steel reduces waste and allows the material to be reused in future construction projects. Throughout the entire girder removal process, strict safety procedures are enforced. Workers wear full protective equipment, and supervisors coordinate each cut and lift. Clear communication between crane operators, excavator drivers, and ground crews ensures that every stage of the operation proceeds smoothly. By methodically cutting, lifting, and removing each steel girder section, the bridge is dismantled in a controlled and efficient manner. This step-by-step approach prevents uncontrolled collapse and allows the demolition team to safely remove the bridge's main structural elements while minimizing risks to workers and surrounding infrastructure. The Colmar Rail Shear RP2000 is presented as a powerful and reliable hydraulic cutting solution, developed specifically for railway maintenance, dismantling, and modernization works. Designed and manufactured by VTN Europe, This heavy-duty attachment is engineered to be mounted on excavators ranging from 21 to 35 tons, making it well-suited for demanding rail demolition environments. The RP2000 stands out for its exceptional durability, as its entire structure is built from hardox and heat-treated steel, ensuring high mechanical strength and long service life even under continuous heavy loads. At the heart of the shear is a large hydraulic cylinder capable of delivering up to 139 tons of cutting force, allowing it to effortlessly cut end-of-life railway rails with a mass of 70 kilograms per meter and above. A high-flow speed valve further enhances productivity by reducing cycle times and enabling faster, more efficient operations on site. To increase versatility and reduce maintenance costs, the shear is equipped with 4 times reversible and interchangeable blades, which extend blade life and minimize downtime. The hydraulic cylinder is fully enclosed and installed in an overturned position, offering excellent protection against impacts and accidental damage during operation. For maximum maneuverability, the RP2000 features an oversized planetary gear-driven 360-degree rotation system, allowing precise positioning and smooth handling in confined or complex working conditions. Specifically designed to cut standard rail profiles such as UIC60, the Kalmar Rail Shear RP2000 is an ideal tool for efficient, safe, and modern railway infrastructure projects. The LD41P is a portable rail drilling machine developed by Sember and specifically designed for professional railway applications. This internal combustion drilling unit is engineered to deliver consistent and precise holes directly on installed rails, even under harsh outdoor and all-weather conditions. Thanks to its compact design and reliable performance, the LD41P is widely used in track maintenance, signaling installation, and railway electrification projects. The machine is powered by a 4-stroke gasoline engine with a displacement of 35.8 cc, typically supplied by Honda. It produces approximately 1 kilowatt of power, or 1.3 horsepower, at 7,000 revolutions per minute. This output ensures stable drilling performance while maintaining efficient fuel consumption. The LD41P supports a wide drilling range, using broach cutters from 13 to 40 millimeters in diameter on rails up to 50 millimeters thick. When equipped with special spiral drill bits, it can drill diameters from 7 to 27.5 millimeters on rails up to 45 millimeters thick. One of the key features of the LD41P is its DBGF2 clamping system. This moving arm device securely fixes the machine to the rail web or flange, guaranteeing accurate alignment and safe operation. The built-in coolant system, consisting of a reservoir and pump connected by a quick coupler, provides continuous lubrication and cooling during drilling. Designed for one-man operation, the LD41P uses a manual pull rope start and an automatic centrifugal clutch. With a total weight of around 19.5 kilograms, the machine remains easy to transport while being compatible with rail profiles ranging from 43 to 75 kilograms per meter. Over the Christmas period in December 2010, a remarkable civil engineering operation was carried out in Battersea, South London, where Poupart's Bridge 18 was replaced after more than 120 years of service. This structure, located on a highly strategic section of the railway, had originally been built during the Victorian era, and since then it had continuously supported heavy daily traffic, while the surrounding network evolved significantly. As a rail-over-rail bridge, Poupart's Bridge 18 carries important lines that link Clapham Junction with London Victoria, meaning that any intervention directly impacts one of the busiest rail corridors in the United Kingdom. Because of this strategic location, opportunities for engineering access had always been very limited. Routine maintenance activities were difficult to arrange, and complete reconstruction was even more challenging. Consequently, the decision to replace the bridge required a long period of coordination between the contractors and the railway operator. During 12 months before the actual possession, BAM, Nuttall, and Network Rail conducted intensive planning, logistics preparations, risk assessments, engineering surveys, and coordination with train operating companies, local authorities, and service providers. The objective was to design and execute a replacement that would be completed safely, accurately, and within a very narrow time window, all while minimizing disruption for passengers during one of the busiest travel seasons of the year. The site constraints presented numerous engineering difficulties. Working above an active railway corridor meant that the structure could only be removed once the tracks underneath were taken out of service, and this was possible only during a planned blockade. In order to avoid affecting weekday commuter services, the operation was scheduled over the Christmas holiday period, when passenger numbers are relatively lower. Nevertheless, the available time remained extremely short. Therefore, all construction activities, including preparation works, temporary protection, bridge removal, and installation of the new decks, had to be executed on a 24-hour basis for several consecutive days. Approximately 200 personnel, including engineers, crane operators, riggers, steelworkers, and safety supervisors, worked around the clock throughout this period. Heavy lifting equipment was assembled on site well in advance, and railway possessions were carefully synchronized so that no minute of the blockade was wasted. The old Victorian structure, although historically significant, no longer met modern loading requirements and presented challenges in terms of durability. It was dismantled in carefully controlled stages, with special attention paid to protecting both the underlying railway and the surrounding infrastructure. Once the old bridge components were removed, the installation of the new structure began immediately. The replacement bridge had been prefabricated beforehand to reduce installation time. Large steel segments were delivered to the site, positioned using powerful mobile cranes and secured by teams operating day and night under strict safety procedures. Precision was essential, as the new structure had to align perfectly with existing track geometry and ensure correct load transfer. The site team also installed new ballast, track components, drainage elements, and other ancillary systems. Weather conditions further complicated the project. December 2010 was marked by particularly cold winter temperatures and snowfall across the UK, requiring additional safety precautions. Despite these challenges, the workforce succeeded in keeping the site operational, thanks to constant monitoring and continuous coordination between teams. By the end of the Christmas possession, the bridge installation was successfully completed within the required schedule. Trains were able to resume operation as planned, proving the effectiveness of the detailed preparation carried out during the previous 12 months. The replacement of Poupart's Bridge 18 significantly improved the reliability of this part of the network, ensuring long-term structural capacity and reducing future maintenance demands. Overall, the project stands as a demonstration of how meticulous planning, modern construction methods, and collaborative teamwork can deliver major railway infrastructure upgrades within extremely restricted timeframes. It also highlights the importance of choosing strategic possession periods, such as Christmas, to minimize passenger disruption while implementing essential engineering work. Through the efforts of BAM Nuttall, Network Rail, and more than 200 dedicated workers, a 120-year-old Victorian structure was efficiently replaced, securing the performance of one of London's most critical railway links for decades to come. Over the past few years, the electrification of the Bristol to Cardiff railway line has transformed this key transport corridor, modernizing infrastructure and improving service reliability. The project began with preparatory works around Chipping Sodbury Tunnel, where engineers surveyed and reinforced structures to ensure clearance for overhead lines. At Patchway Track and Tunnel, crews worked continuously to install masts and overhead cables, carefully coordinating with ongoing train services to minimize disruption. Between Patchway and Severn Tunnel Junction, known locally as the Patchway Gap, teams dismantled old signaling equipment and replaced it with new electrification-ready systems. At Rogiet Road Bridge, workers raised the bridge canopy and fitted support brackets for the overhead line equipment, a complex task requiring precision engineering. Further along, at Llandefany Road Bridge and Huggett's Road Bridge, specialist crews strengthened the existing structures to carry new electrical infrastructure. These bridges were critical pinch points where careful planning ensured both safety and compliance with new clearance standards. In Newport Station, the electrification works brought major upgrades to platforms and canopies. New mast foundations were laid and overhead lines carefully tensioned above operational tracks. At Bridge Street, Newport, and later at Splot Road Bridge, Cardiff, the installation of gantries and final line stringing finished the last stages of the electrification system. By upgrading these key locations, the project has enabled faster, greener, and more efficient electric train services between Bristol and Cardiff, supporting regional connectivity for years to come. The construction process begins at the welding plant, where prime rails are carefully loaded and handled using specialized lifting equipment to prevent deformation or surface damage. These rails are then fed into the flash butt welding line, where individual rail sections are electrically welded end-to-end to form long welded rails. This method ensures precise alignment, strong joints, and consistent rail geometry suitable for heavy-haul railway operations. Once welding is completed, the long rails are inspected and prepared for transportation to the track-laying site. At the construction corridor, the first layer of ballast is spread along the prepared formation. This initial ballast layer provides drainage, load distribution, and a stable base for track components. Following this, rail unloading operations begin, with long welded rails and concrete sleepers delivered and positioned alongside the track using rail-mounted or road rail machinery. Sleeper and rail laying is carried out systematically, ensuring correct spacing and orientation. The rails are then placed onto the sleepers and temporarily supported before fastening. Rail welding activities continue on site to connect rail sections into a continuous track. Fastenings are released at specific locations to allow controlled rail movement during welding. Flash butt welding is applied where long rail strings are joined, ensuring high-strength welds with minimal defects. After welding, the welds are ground to restore the rail head profile and ensure smooth wheel-rail interaction. Once the rails are fully connected, ballast filling begins. Additional ballast is distributed to encapsulate the sleepers and rails, improving track stability. A topographic survey is conducted to verify track position, elevation, and alignment against design specifications. The second layer of ballast is then added, followed by ballast profiling to shape the ballast shoulders and ensure uniform support. Track leveling, alignment, and tamping operations are performed using automated tamping machines to correct vertical and horizontal geometry. To enhance long-term stability, track dynamic stabilization is carried out, simulating the effect of train loads. Final ballast profiling and track brushing refine the ballast shape, while vacuum cleaning removes excess sand and fine particles from the track structure. The de-stressing phase follows to control internal rail forces caused by temperature variations. Fastenings are released to allow the rails to move freely. Rails are then cut at designated locations to establish the required neutral temperature. Rail pullers are laid and installed to adjust rail length precisely before final welding. Alumino-thermic welding is used to permanently reconnect the rail ends, producing strong, durable joints directly on site. After cooling and finishing, the rails are refastened, completing the stress-free continuous welded track ready for service.